Today we're going to practice a free response question together. And the free response question we're trying is question from 2019, so just last year's FRQ, and this is question number 1. The topics of this question are going to be on electrostatics and on magnetism. So we're going to be taking a look, kind of comparing electric forces and magnetic forces in this free response question. So let's try it. So here we have a particle with a positive, a plus Q charge, that just means some amount of charge, is traveling with a constant speed to the right and in the plane of the page. The particle is approaching the region shown by the dashed box that contains a constant uniform field. The effects of gravity are negligible. In the figure below, we're going to draw the possible path for the region if it contains only an electric field directed towards the bottom of the page. So our electric field is going towards the bottom of the page, and our particle is positively charged. And we know that a positively charged particle will follow the field lines. If it was a negatively charged particle, it would go against the field lines. So basically, it's going to enter here like this with a velocity. And our velocity is going to be to the right here, and our force is down. Remember, if it is a positive charge, the field and force are in the same direction for the electric field, and if it's a negative charge, its force will be in the opposite direction of the field. So we have a particle that's only force is directed downwards, and its velocity is this way. Not quite a free response question, but I want to compare this kind of to gravity, that the only force is directed down, and our particle kind of makes this path. So our particle is going to make like this kind of parabolic path, just like it would for the force of gravity, because our only force is directed downwards. So there we go. In the figure below, draw a possible path if it contained only a magnetic field out of the page. So for magnetic field directed out of the page, like this, we're going to use our right-hand rule. The velocity is our thumb. Our thumb points this way. Our field comes out of the page, and my palm is going to show me the direction of the force. So for this, my force is going to be directed downwards. So my particle experiences a downwards force from the magnetic field and a velocity like this. But the difference is here that the direction of that force changes as our particle is moving in this magnetic field. For our electric field here, the direction of the force does not change. It's always directed downwards, or velocity does not affect force. Or the direction of the velocity does not affect the force. For a magnetic field, our direction of the velocity changes the force. So as soon as our particle enters and it starts to curve, the direction of the force also changes. So the difference here is that this one is going to be much more circular looking. So this one should be parabolic, and this one should be circular. This one should look very similar to gravity, and this one should look like circular motion. And that's just because here the velocity does not affect the direction of the force, and here our direction of our force changes. So when our particle's over here with the velocity this way, the force is this way, and so on. So the directions are changing. Let me just erase those extra lines. Remember, if this is a real free response question, you are only going to make sure you have things you want graded on your diagram, no extra things on your drawing. So we kind of already answered part 3 here. Part 3 says, which situation is more similar to that for a projectile only under the influence of gravity? And that's going to be scenario 1. Part I, or our electric field. And we can say that that's because the only force is downwards. and that our force does not change direction. And let's see. I'm going to look at our scoring guide real quick, kind of see. And we can also put the kind of our shape is parabolic. So let's just recap on our scoring guide. If this was the real national exam, which it was in 2019, I think that this one was worth 2 points. This one was worth 2 points, and this one was worth 1 point. Don't know if you can see that. It's worth 1 point. So our 2 points here for part A was that for part A, we have for a curved path that is initially horizontal, and then for our path, it reaches the edge of the region. So basically, kind of just the shape of this is kind of parabolic, and you drew it all the way down to the edge. You didn't kind of stop it over here or something. Then for part 2, our points are for a curved path, not more than a semicircle. So basically, this should look like a semicircle, and it reaches all the way to the bottom here. It doesn't stop somewhere over here. And for it to flex towards the bottom of the page. So you didn't draw it going upwards like this, but it went downwards. And then if we look at part 3, 1 point for indicating the motion of the electric field is similar to a projectile because the force or acceleration is always down, and the shape is parabolic. So it's kind of our scoring for the first 3 parts. Let's do part B, which is our paragraph length response. Another region of space contains an electric field directed towards the top of the page. I'll make it so we can see this drawing. And a magnetic field directed out of the page. Both fields are constant and uniform. A horizontal beam of protons with a variety of speeds enters the region as shown above. Protons exit the region at a variety of locations, including points 1 and 2 on the figure. So these are our 2 points we're kind of looking at. In a coherent paragraph length response, explain why some protons exit at 1 and others at 2. So basically, we're going to be comparing the magnetic field and the electric field. So first of all, our particles are going to be experiencing a magnetic force that is directed, this is going to be our electric field is going to be directed up. We're going to call this our force. We'll call it our force electric will be directed towards the top of the page because our electric field is to the top, and for a positive charge, it will have a force in the same direction as the field. Our magnetic force will be directed to the bottom of the page. So same thing, right hand rule, our magnetic field is out of the page, the velocity is to the right, and our palm points down, so we're going to have a magnetic force downwards. So let's think about what these 2 things depend on. We could find the electric force by doing kq over r squared, or kq1, q2 over r squared, or we could do kind of the electric field strength times q, whatever the charge of those protons is. To find the magnetic force, we're going to use qv B. And you're going to see a big difference here. This depends on the field strength and the charge. This depends on the magnetic field and the charge and the velocity. And the reason that's so important is it tells us that our protons enter with a variety of speeds. So what that means is, if you have a particle whose speed is at some kind of perfect balance, you're going to end up with equilibrium. And your particles for equilibrium would exit right here, straight through, because there's no net force acting on them. Fast particles above some speed that we can't really measure without having numbers, are going to experience a larger magnetic force. So fast particles are going to have a larger magnetic force than electric force, and they're going to be deflected down, aka at point 2 or below or whatever, something below my green dot there in the middle. So our faster particles are going to be deflected at 2. So 2 must be all of the particles that are moving above some certain speed, versus slower particles are going to experience a greater electric force than magnetic force, and they're going to be deflected up because their net force is up, and those are going to exit at number 1. So the difference here is the faster particles will experience a larger magnetic force, and slower particles will experience a larger electric force, because magnetic force depends on V and electric force does not. So let's just take a look at the scoring guide for this. I didn't really write a paragraph, but hopefully you can kind of connect how you would write a paragraph here. So our scoring guide said, for indicating that initially the electric and magnetic forces are in opposite directions, so indicating that your electric force and magnetic force, one is up, one is down. For indicating or implying that the magnetic force is affected by speed, but the electric force is not. So basically relating it to an equation. An important thing with any sort of problem like this is thinking about what is your relevant equation here. So I reference my relevant equations for indicating that different paths occur as a result of addition of forces. So basically explaining like the fast particles have a net force down, or slower particles have a net force up. So talking about the net force on the particles. For indicating that slower protons exit higher, faster protons exit lower. So something about the faster particles are deflected to 2, slower particles are deflected to 1. And then usually for our paragraph length, we have a point for having a logical, relevant, internally consistent argument that addresses the question and follows the guidelines. AKA, this would not get that point because I did not write it in paragraph form, but if you wrote this in a nice, beautiful paragraph form, and you were internally consistent, you were relevant, you didn't go off on a tangent about something, you would get that point. So this was free response question number 1 from the 2019 AP Physics 2 exam. Hopefully this helps you review before your AP Physics 2 exam.